So this is going to be a demonstration of ferromagnetism and also something called the Curie temperature. So what we're going to use in this demonstration is this coin. So this coin is a Canadian nickel, and you can see on the back the beaver, so it's Canadian. And we're going to compare that in a moment to an American nickel. It looks like this. So American nickels, it turns out, in the recent decades don't have a lot of nickel in them because nickel is kind of an expensive element to mine. They have a little bit of nickel, but they're mostly made of copper. And copper is not a magnetic material, but nickel is. Nickel is what's known as a ferromagnet. On the other hand, Canadian nickels are mostly made of nickel, and so they're pretty magnetic. They're pretty strongly ferromagnetic. So what it means to be ferromagnetic is simply that the atoms of nickel each, in fact, are themselves tiny magnets. And in a ferromagnet, it's fairly easy to line up all of the little atoms, which each are tiny magnets, to make a pretty strong overall magnetic material. And in some ferromagnets, they're actually naturally magnetized without doing anything to them. You can actually get some magnetic effect. So for example, if this were magnetized, I might be able to hold up a paper clip, right? But it doesn't work. Okay, it doesn't pick up a paper clip. So, but some ferromagnets are actually naturally magnetized. So what we're going to do to magnetize this nickel is we're just going to take a magnet, which is magnetized, and stick it on to the Canadian nickel. All right, because it's a ferromagnet, it sticks. And so what's happened now inside the coin is that all the atoms are lined up, and we've magnetized the coin itself. And now the coin itself, is strongly enough magnetized that it can hold up a paper clip. All right, I'll just compare that to an American nickel, which has a little bit of nickel in it, but not enough. So, I can't even make it stick to this bar magnet. Okay, so now we know a little bit about what ferromagnetism is. The second part of this demonstration, I'm going to bring in a blowtorch. And I'm going to start the flame, and I'm going to show you something about the blowtorch. So I'm going to try to keep my body out of the way here. I'm aiming the blowtorch away from the table and away from the camera. So now, I'm going to take my Canadian nickel, I'm going to put the coin into the flame, and I want you to watch. The flame is heating that coin. I'm going to do it again, but I want you to notice something else. Hopefully you've noticed that I actually had trouble picking up the coin from the floor with the magnet. Try one last time. So this time I was able to pick it up. See if I can show you one more time. So now I'll pick it up. I picked it up on the third or fourth try. All right, so what was the point there? You can think about why that coin fell down from the magnet after it got very hot, but it has to do with what was causing the magnetization of the coin in the first place, which was the atoms of the nickel had become aligned, when I put it on the magnet. But what happens when I heat something to a very high temperature? Well, we know that the atoms start moving faster and their motion becomes more random when the temperature gets high. And so there is a particular temperature for any ferromagnet, and that's called the Curie temperature. And at that temperature, there is a transition from an organized state where all the atoms are lined up at lower temperatures to a disorganized state where the atoms are truly pointing in random directions, and so their net magnetic field is then basically zero. So that's kind of a phase transition analogous to melting a substance. Although we didn't really melt the nickel, nevertheless we made its atoms become disorganized in that way. So that is a magnetic phase transition that ferromagnets have, and the temperature where that happens is called the Curie temperature. So now you know what the Curie temperature is.